Okay, so we are going to be going over the Chapter 6 discussion questions, question by question, because I'm worried that we won't get through it in class. So this way you'll have all the answers in order to study for your midterm. Be studying this in the Chapter 5 ones. But a lot of what we talked about in Chapter 5 we built off of for Chapter 6. So keep that in mind. So the first one just says, what is the meaning of the term polar when talking about chemical bonding? So there's two types of things that we can be talking about when we're talking about polar. We could be talking about chemical bonding, or we could be talking about molecules. Obviously, in this case, we're talking about chemical bonding, and the way you get a polar charge whenever we're talking about bonding is just the uneven distribution of the charge. Okay. Remember where one is way more electronegative, meaning that the bond is going to point or pull towards the delta negative side, and then you'll have the delta positive end. And that's just meaning that one side is way more electronegative. So let's write electronegativity up here, because it's specifically talking about electronegativity and not necessarily like the magnitude of the charge. Okay. For number 2, it says distinguish between polar covalent and polar and non-polar covalent. So both of them are covalent bonds, but they are different. One's polar, one's non-polar. One obviously has poles and the other doesn't have poles. So the polar covalent is just the unequal attraction for electrons. And I can't write very small. Unequal attraction of electrons and one atom is partially negative and the other one is partially positive. So one atom is neg and then one then is pos. Okay. And that's for polar covalent. And then non-polar covalent, they do not have poles. There's not an unevenness to it because the electrons are shared equally by bonded atoms. That's the definition. Equally, I'm just going to do an equal sign, shared equally by bonded atoms. You do not have to have this verbatim. So if you want to write the word equals, go for it. It can't. It's hard. Okay, so remember like the way I talked about it in class with polar and non-polar is that like if it is non-polar, you're like equally in the middle, like the equator, and you're not closer to either of the poles. But when it's polar, obviously a charge is pulling it closer to one of the poles, making it polar. Okay, so on this next chart, you had to go to page 153 in your book to find the electronegativities. Page 153. So like for hydrogen, the electronegativity is 2.1. And then iodine is 2.5. So if I did that, I'd get a negative number, but make it positive, just swap it around, and you get the answer is 0.4. Okay, so that's all I needed was 0.4, but I'm just showing you how I got it. Okay, the electronegativity for oxygen is 3.5. The electronegativity for sulfur is 2.5, so there's a difference of 1.0. If you need help on figuring out how to get these numbers, just go to that page in your book and ask me for help and I can help you. But it's literally just the difference in electronegativities. And then remember, to determine the bond type, we have to look in the difference in electronegativity. So a difference of 0 to 0.3 is nonpolar covalent. A difference of 0.4 to 1.7 is polar covalent, because that charge is then pulling it towards the poles. And then greater than 1.7 is ionic. So I'll just fill in the rest of the chart. So there's the different bond types. Make sure you know how I got those. Those will be a question on your test. And then to figure out the more negative atom, we can use the chart again, or just use our trend in the periodic table. So remember, if we're looking at the periodic table, the trend increases going that way. Okay, so looking at hydrogen and iodine, we shouldn't even have to consult the chart, because it's going to be iodine. Sulfur and oxygen is going to be oxygen, bromine, chlorine, sulfur, and carbon. Okay, so you should be able to figure that out just like from the general trend, but if you have to consult it a little, it's not a huge deal. Okay, moving on to number 4. It is talking about the lattice energy of sodium chloride is that negative 787.5 kilojoules per mole. The lattice energy of potassium is negative 715 kilojoules per mole. In which compound is the bonding between ions stronger? So remember, I want you to think back to that graph that we did talking about the 2 hydrogen atoms, where it looked like this very roughly. So it went backwards and looked like this, and then it dropped and then went back up like that. So at this point, remember, it started at 0 and like this went to like, I don't even remember now, like 400 something, negative 400 something. And at that point, at point C, it was the most stable, meaning that the attraction was stronger. It's not going to go and form other compounds. It is strongest at that point when it has a lower potential energy. And so lattice energy is kind of just talking about its ability to form those lattice bonds. So in this case, which has the more negative potential energy, which is more stable, which is least likely to do things because it doesn't have the energy to, it's that one. So it is sodium chloride. And the reason is because the energy is more negative, so it's more stable. The lower the potential energy is, equals more stable. Okay. Number 5 asks, what is a molecule? So remember, a molecular compound is made up of nonmetals. So it's just the neutral group, meaning it doesn't have a charge. Because if you think about it, ions or ionic compounds have a charge. Molecules don't. Neutral group of 2 or more atoms. Atoms, typically nonmetals. Not always, but typically nonmetals held by covalent bonds. So obviously ionic bonds are held, or ionic compounds are held by ionic bonds. In this case, covalent bonds hold molecular compounds. That is also super important to know. Hint, hint. Okay, number 6 says, describe the octet rule in terms of noble gas configuration and potential energy. So the whole thing with the octet rule is that it wants 8 in the outermost energy level. So basically it wants full outer S and P orbitals, because those are always going to be your highest energy ones. Because remember, if you're doing like one further on down, it'll be like 5s2 and then go back up to 4d10 and then back down to 5p6 or whatever. And so the S and the P orbitals are always going to be the ones in the highest energy. So it wants a full S and P orbital. And if we did the electron configuration for a noble gas, they'd have obviously a full S and P orbital, meaning that they, and then there are how many electrons in the S orbital? 2, and then how many in the P? 6, for a total of 8 valence electrons. And so in noble gases, there's no need to gain, lose, share electrons. And if that's the case, is their potential energy going to be low or high? If they do not need to gain electrons and they're very stable, they have a very low potential energy, because as we know, group 18 is not going to go out and form. They're extremely unreactive. Okay. Number 7 says determine the number of valence electrons in an atom of each of the following elements. That one we should just know to look at our handy dandy periodic table and look at what main group it's in. If you need extra help with this, make sure you know how to do it. It is super important and it will be on your test. So if you don't know how to do it at this point, you need to be asking me. So make sure you got those right. Again, using the periodic table, you will have to know how to do that. Okay, page 2 starts with number 8, and it says, in a Lewis structure, which atom is usually the central atom? Explain why. So typically, it is going to be carbon. And if you think about carbon, and we're explaining why, how many valence electrons does carbon have? It has 4, meaning that it can easily form 4 different bonds, and then it can fill its octet. So basically, it's willing to give up or share its electrons so it can fill its octet. Easily shares electron to fill octet. Basically, carbon is ready to form bonds with up to 4 atoms, so it'll have that octet. Because of its 4 valence electrons, it can give 1 and get 1 from another one to form that bond, and then it's sharing 2. We know how that works. And then it, if it's not carbon though, if carbon is not in the atom, then it's just, so if carbon's not there, if no carbon, it's the most electronegative element or atom. Okay, so like say you had fluorine with hydrogen and bromine or something. Obviously the fluorine's going to be in the middle. Okay. Number 9 says distinguish between single, double, triple covalent bond by defining each and providing an illustration of each type using fake atoms, basically. So the main thing for a single bond is obviously that they share one electron pair. So pair, there's 2 electrons in a single bond. An example of this using actual atoms is going to be H2O, where you have hydrogen and then oxygen and then hydrogen again. So here we have 2 single bonds. A double bond is going to be made by forming, you guessed it, 2 electron pairs. A common example of this is in CO2, where you have O, and then we're not going to worry about the extra electrons because we're missing some on all of them. And then triple is obviously 3 electron pairs. And a triple bond, typically nitrogen forms triple bonds. So here, okay, I'll just go add the dots. So we have nitrogen has 2. This one will have 2 lone pairs on each one. And then this one will have 2 also. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4. Yep, that's right. Okay. Okay. Going on to number 10. It says, for Lewis structures, how is the need for multiple bonds generally determined? So let's take this example up here, CO2. So if I were to write C, it has 4 valence electrons, as we know, and oxygen has 6. So 1, 2, 3, 4, 5, 6. So basically, even if we put carbon and oxygen together and share those, there still be those. So let's say they're sharing those 2. Okay, same thing over here. 1, 2, 3, 4, 5. So basically, not everything's happy because they don't have, number 1, they have unshared electrons, or they have like lonely electrons over here, and because there's no octets here. So carbon only has 2, 4, 6. Oxygen only has 2, 4, 6, 7. So there are 2 things. The main one being there's no octet. On the atom, and 2, there are unshared electrons. Okay. Number 11 wants you to use the electron dot structures to demonstrate the formation of ionic compounds involving the following elements. Okay, so in this case, let's see, you have sodium with 1 valence electron and sulfur. Ooh, okay, let's pick red. And sulfur with 6. Okay. So, in order for sulfur to get an octet, how many electrons does it need? It needs 2. So how many sodiums is it going to get or form bonds with? 2. So in this case, in this scenario, is it going to be easier for sodium to get 7 or get rid of 1? And then is it going to be easiest for sulfur to get rid of 6 or gain 2? Obvious answer. So sodium is actually going to give up its electron and form a sodium ion. And if something gives up an electron, it gets a positive charge. So you have one sodium ion plus another sodium ion plus sulfur, which now has an octet. It's happy, and it has a 2- charge. And if you look at your handy-dandy periodic table, you will notice that that is the charges for the columns. Okay, let's try it for B. So calcium has 2. Oxygen, as we know, has 8. 6. What am I saying? Has 6. So here, in order to get an octet, how many electrons does oxygen need? It just needs 2, so it only needs 1 calcium ion. So in this case, calcium is going to lose its 2 electrons to get a positive 2 charge, plus oxygen with its octet now has a 2- charge. And let's look at aluminum. Aluminum has 3 valence electrons, and sulfur again has 6. 2, 3, 4, 5, 6. Okay. So in this case, sulfur only needs 2 of aluminum's electrons, but aluminum's still going to get rid of all of them. It'll pawn that other electron off on someone else or something else, so that sulfur has a 2- charge and a full octet, but I can't really draw it. Okay. Okay, let's move on down here to the Lewis structures. At this point, I'll work out one of them, and then I'll just do the rest, and you should be able to, for the love of everything holy, do the others. If you are just like trying to check them, great, that's what I'm here for. But if you need help figuring out how to work them out, please come and ask me. You will have to do this on your midterm. So on A, it talks about it containing 1 carbon and 4 fluorines. So we know that what's going to go in the middle, the carbon. Carbon has 4 valence electrons. And then fluorine, we have 4 of them. So we can assume they'll be around the carbon. And fluorine, we know, has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. So that these 2 right here are going to form a bond. Just one. Just a single bond. And the rest of the electrons, the 6 of them, will be around the fluorine. Okay, and if we count, fluorine is contributing 1 to this bond, so it has 1, 2, 3, 4, 5, 6, 7, which is how many valence electrons it has. And then in its possession total, how many electrons does it have? 2, 4, 6, 8. It has an octet. On this next one, well, hydrogen is never going to be the central atom. Let's look at C, where it talks about 1 nitrogen and 3 iodine. Even if you don't know the electronegativities, could iodine with 3 of them possibly be in the middle? No. So I'll write out the Lewis structures and you can check them. And if we go back through and double check, you can tell that all of these atoms are happy because they're filling that octet, with the exception of hydrogen. Okay, so let's look down at 13, which challenges us a little more. Okay, so for A, it says, or it has O2. So we have oxygen with 6. We know it's going to form at least a single bond with the other oxygen. So if you start off with 6 valence electrons and contribute just 1 to this bond, then you have 5. So let's draw those in. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Not everyone is happy, so those 2 atoms, or electrons, excuse me, are going to come in to form a double bond, and then those will kind of adjust. Okay? B is nitrogen, which has 5 valence electrons. So we can assume it's going to at least form a single bond, leaving 1, 2, 3, 4. 1, 2, 3, 4. So this electron and this electron are not happy. This electron and this electron are not happy, meaning that all of them will come in to form a triple bond. Remember nitrogen? Nitrogen is extremely likely to form a triple bond, but they'll still have a lone pair like that. Okay. C. Okay. For C, we have C and O. This next one is a bit trickier. So let's go ahead and do the electron dot notations for carbon and oxygen. Not the best place. Okay, hang on. Let me draw it further on down. Off the page, but y'all have more room because y'all are able to write smaller. Okay, so C is carbon 1, 2, 3, 4, and oxygen 1, 2, 3, 4, 5, 6. Okay, so obviously none of the electrons on carbon are happy. This electron and this electron are not happy. So those are going to bond together. The over here, come over here, that one and that one, so that we get a double bond. But we still have 2 on carbon that are unhappy, and these 2 on oxygen. But we could just take this little electron down here and put it up here, and then everything's great. Let's check. So carbon has 2, 4, 6. Oxygen has 2, 4, 6, 8. So in this case, oxygen's fine. Oxygen's content. But carbon, on the other hand, is not happy because it only has 2, 4, 6 electrons, and it needs 8. So in this case, these 2 electrons are going to basically be taken over by the carbon. And oxygen is going to contribute both of those to the bond, or to the bond, so that carbon has that, and then oxygen just has 1 lone pair. And so now they're both happy. But in this case, carbon is contributing only 2 electrons, and oxygen is contributing 1, 2, 3, 4 electrons to the bonds. So a bit different than what we've done, but carbon wasn't happy because there was no octet there. Okay, let's try to squeeze in D down here. Is another tricky one. Okay, so we know sulfur is going to be in the middle, and then we have oxygen. So sulfur has 6 valence electrons. So does oxygen. So if they each share 1 for a bond, they're not ever really going to come to a resolution. So it's going to be something also weird. So if sulfur's contributing 1 to each of those, and it has 2 left over. This oxygen would have 6 left over. Well, actually, it'd only have 5. 5 left over. And then also 5 over here. Okay. So the sulfur's doing fine because it has an octet, but the oxygens are not okay because they do not have an octet. So what's going to have to happen is that instead of right here, this oxygen contributing 1 electron, sulfur is actually going to contribute both of the electrons to this. So the oxygen still has 6, and sulfur, both of those are contributed from sulfur. So I'm going to write that from sulfur, if you can read that. And then this one has 1 I can't. Okay. So to this bond, the sulfur is contributing 1 to this bond. Sulfur is contributing 1, leaving this lone 1, so that this lone electron and this lone electron over here want to pair together to form a, you guessed it, double bond, so that you have oxygen with its 6 because it's not contributing anything to that bond. And then you have a double bond with oxygen, and it has 2 left over. And then sulfur has a lone pair left over. Okay, so let's double check and make sure everyone's happy. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. And on this problem, it does say show resonance structures if they exist. Yippee-ki-yay, they exist here. So that you could also have this and a double bond, so that the double bond is basically just swapping sides. Okay, both of those would be correct. Okay, moving on to ionic compounds. Ionic compounds basically happen because of the equal and opposite attraction of their ions. So they're composed of cations and anions. Of equal and opposite charges. So like sodium chloride, sodium has a 1 plus charge, chlorine has a 1 minus charge. They are equal and opposite because opposites attract. Okay, it says in general, how do ionic and molecular compounds compare in terms of melting points and boiling points? So, ionic compounds typically have higher melting points and boiling points because of the stronger forces between particles. Okay, number 16 says, how do the properties of metals differ from those of both ionic and molecular compounds? So basically there can be ionic bonds, there can be molecular bonds, and now these are talking about metallic bonds. So metals as we know, are better heat and electrical conductors. They're more easily deformed, so to be malleable or ductile. More easily deformed. Shiny. And this is all because of their outer orbitals, empty, because of empty outer orbitals and sea of electrons in those outer orbitals. So remember, like whatever it does have, they don't follow their normal wave pattern. They just kind of like float in the outer orbitals. Number 17 says, what specific property of metals accounts for their unusual electrical conductivity? This is mainly because of their highly mobile electron within orbits. So remember, because like the electron can go in and out of those energy levels, those ions are freely flowing, meaning they can conduct that electricity very well. And the highly mobile electron within the orbitals is because of the sparsely populated outer orbitals. And that's the answer to 18. So basically every property of metals comes back to the fact that their S&P orbitals are barely full or full of electrons at all. Okay, number 19. It says, how is the VSEPR theory used to classify molecules? And it does it on shape because based on number of bonding electron pairs and lone atoms. And remember, in the VSEPR theory, they want to be as far apart as possible. So we'll just say being repulsed by each other. Number 20 says, what are intermolecular forces in general? How do these forces compare in strength with ionic and metallic bonds? So remember, we talked about intermolecular forces, and they're not necessarily bonds. They're just weak forces. So they are forces of attraction. Between molecules. And they are weaker than both of those bonds. Weaker than ionic and metallic bonds. Number 21 says, what is the relationship between electronegativity and the polarity of a chemical bond? So basically, the larger differences in electronegativity I'm abbreviating, the greater the polarity. And if you think about it, if one is way more electronegative, it's going to be way more charged, meaning that the pole is going to be stretched even further towards the other end. Number 22 says, what are hydrogen bonds? So remember, hydrogen bonds aren't technically bonds, they're intermolecular forces. And it's a dipole, 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 intermolecular force between hydrogen and highly electronegative atoms like nitrogen, oxygen, fluorine. Okay, it says give 2 specific examples mentioned of hydrogen bonds. We didn't get to mention the other one. We'll do it after your test. So basically, we mentioned the bonds between strands of DNA. That will be a question. And surface tension. So the reason that certain bugs or animals are able to slide across the surface of water because the surface tension, the intermolecular forces keeping the water molecules together, we kind of talked about it. Remember, I'll draw this down here. Maybe it will benefit you, hint, hint, on the test. So let's say we have water. So we have oxygen, that's hydrogen, oxygen, hydrogen. Remember, these are positive, that's negative. So the arrows look like that. So the oxygen's not going to be attracted to other oxygens, it's going to be attracted to other hydrogens. So when you have enough of these, that's going to be attracted to a hydrogen. And then there's just this attraction between them. It doesn't form bonds. Really, it's just this intermolecular attraction. So there would be a hydrogen here, oxygen, hydrogen. You get the gist. And because of water structure, where it's bent like this, where oxygen and hydrogen, they're able to really maneuver around each other. It's not something super complicated and latticed together. Okay, next page. Okay, so it's saying, for each of the following polar molecules, indicate the direction of the resulting dipole. So for A, we just have to look at which is more electronegative, hydrogen or bromine. In this case, it is bromine. Give it an arrow like that. B, pretty easy too. Iodine's more electronegative. So the charge is being pulled in that direction. Okay. Number 25 says determine whether each of the following bonds would be polar or nonpolar. This is where you just have to look up the differences in them. And so on the first one, the differences in hydrogen is obviously 0, so it's nonpolar. Same thing over here, nonpolar. And then the rest are polar. But make sure, for the love of everything holy, you know how to do that, because it will be on your test. Number 26, though, says on the basis of individual bond polarity, and orientation, determine whether each of the following molecules would be polar or nonpolar. So in this case, we're not talking about bonds. It wants to know if the molecules are going to be polar or nonpolar. Okay? So we have to look a lot at the orientation of the molecules. So I already drew water. We know water is polar. Iodine, because of the fact that it's two iodines together, is going to be nonpolar. So if we look at CF4, your carbon is going to be surrounded by 4 fluorines. And are the fluorines going to be attracted to each other? No. So it's not really going to form any different poles. It doesn't have any poles, so this one is nonpolar. D. Let's see. We have a hydrogen and a hydrogen and a hydrogen, meaning that this one is polar because of the differences in charges. And then CO2 is going to be nonpolar because of its double bonds and everything that we know already happens. Okay. On 27, I will pause it, draw them all. You can check them. If you get them wrong, be asking why you got them wrong, okay? These ones are more straightforward, so make sure you're asking if you're still getting confused, because I will say it again, it's going to be on your test. Okay, so like for this molecule, it is going to be linear. For this one, oh wait, I'm missing an iodine on there. Oh gosh. Okay, let's put that guy in. Oh, there's going to be a third iodine. I just didn't see it until now. 2, 2, 2, 2. But you get the gist. That one, since there's 3 iodines, is going to be trigonal pyramidal. This one is going to be linear. This one is going to be trigonal. This one is going to be tetrahedral. This one's going to be linear. On this one, if you put the bromine literally anywhere else, it's fine. As long as, remember, these are like 3D structures, so they're floating around constantly. It doesn't matter really in what order or on what side you drew them. Okay, this next one says, arrange the following pairs from strongest to weakest attraction. So if you think about that chart where it has nonpolar on this end, and then polar, and then ionic, clearly ionic is the strongest. So ionic and ionic is going to be the strongest. Then next is going to be still an ion, but a polar molecule. And then polar, polar, and nonpolar, nonpolar. Number 29 wants you to determine the geometry of the following molecules. Since there are 4 here, we know it's going to be tetrahedral. Since there are only 2 here, it's going to be linear. And since there are 3, trigonal. You didn't even have to draw them. I just wanted you to be able to identify them. Number 30 asks, what type of atoms tend to form the following types of bonding? So what tends to form ionic bonds? Those are both metals and nonmetals. So you could have a metal and a metal, or you could have a metal and a nonmetal. That doesn't look like what that says. Okay. With covalent, those are going to be formed by non-metals only. And then metallic bonds, obviously, are from metals only. Make sure you have those understood. Okay, we're on the back page, finally. And it says draw the 3 resonance structures for sulfur trioxide. So sulfur is obviously going to go in the middle. And then we're going to have the 3 oxygens coming off of it. We know. But again, since sulfur and oxygen both have 6 valence electrons, if they each donate 1, then they're each going to have 5, so they're each not going to be happy. So in this case, sulfur, let's start off with like both of these. In both of these bonds, sulfur is going to donate both of its electrons. And so then oxygen doesn't have to donate any, so it's going to still have its 6. So I'm going to draw that. And then down here, if we did that down here, and we had 6 around this oxygen, the sulfur would not be happy because it would only have 2, 4, 6. So it wouldn't have an octet. So this one down here is going to have to share its electrons. Because sharing is caring. It's going to share those and form its own bond. So that now let's go look and see that everything's happy. So we have 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. And so now since there are 3 oxygens, this could look 3 different ways if we drew it. So we are going to draw the resonance structures because remember, like these electrons that form this bond will bounce up there, and then those electrons will rotate over here, and it's a hot mess of electron exchange. So we'll draw all 3 structures. Let's put the double bond out here now. 2, 2, 1, and 1. Perfect. And then the third one, we'll move the double bond over so that we have an oxygen, oxygen, oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And those are the 3 resonance structures. Number 32 asks, how do ionic and covalent bonds differ? In ionic bonds, the valence electrons, which I'm going to abbreviate, of the less electronegative, which I'm also going to abbreviate, electronegative, atom are donated to more positive atom. So they don't really share them, they are donating them completely. Like in chlorine bonds, valence electrons are shared. That's the key difference. Okay, number 33 asks, how does an ionic compound differ from a molecular compound? So remember, a molecular compound like water, it exists where you can have 6.02 times 10 to the 23rd water molecules because they're each a separate thing, okay? So they are individual units existing on their own. Sure, they're all floating around together, but they're still individual water molecules. But in ionic compounds, remember the sodium chloride that we looked at where it was like the cube, it was like the lattice structure where it's like all like this, except it's 3D, so it's a bigger mess than that. And they're all interconnected. in this, meaning that it's harder to, there's no individual compound, no individual units. Arrangement, there's an arrangement of ions. Okay, so maybe, hint, hint, on the test, I will show you like individual water molecules, and you'll have to identify that it's a molecule. And then I could show you this like lattice structure, and you'll have to realize that it's ionic bonds because of the structure of it. And I'll put a picture on the board while you're doing this. If you've gotten to this point and haven't, someone remind me. But look up there and kind of notice what I'm talking about, the difference. Okay. And then 34 says explain the role of molecular geometry in determining molecular polarity. So bonds can be polar. We've talked about polar bonds. But that doesn't always mean that molecules are polar. So the arrangement of polar bonds in space the molecular geometry determines if the entire molecule is polar. So basically meaning like, can that water molecule reach other things it's attracted to? It can only do that if it is shaped in such a way that they can like fit together like that, right? So if you just had something that was linear, like let's see, diatomic nitrogen, there's no way for it to be attracted to anything else because it's literally just nitrogen and they can't all like fit together, okay? But water is a perfect example of a polar molecule because the way it's bent like this allows the other molecule or the other poles of the molecule be attracted to it. Okay, moving on. It says, what factors affect the geometry of the molecule? So remember, the geometry of the molecule is determined by the VSEPR theory, which is saying that the electrons want to be as far apart as possible. And electrons are held in bonds, so the number of bonds makes a big deal. And the lone pairs of electrons. Okay. Number 36 says, what experimental property directly correlates with the strength of intermolecular forces? So an experimental property is like a property that we can experiment with and determine. So if you had a liquid of some sort, you could experiment on it using these properties and kind of figure out what liquid or what compound it was. So in this case, boiling point is basically the strength of the intermolecular forces. So boiling point is the temperature at which molecule goes from a liquid to a gas And basically, in a gaseous state, all of the intermolecular forces are broken because we know that a gas just fills the volume of the container that it's in. So if the gas goes from like a small bottle to an entire room, it's just going to go throughout the room because there are no intermolecular forces keeping it together. And so if it's stronger if more energy needed to break intermolecular forces and increase the boiling point. Okay, for 37, I'll do what we've been doing. I'll pause it, draw them all. If you need specific help, please ask me. Okay, so if we look through all of these, everyone's happy. Because they've all got an octet. Number 38 says, why does fluorine generally form covalent bonds with great polarity? Because it has the greatest electronegativity. And the greatest attraction for electrons. So meaning it wants all of the electrons. So all those electrons are going to go towards that pole that fluorine has. Okay, and then the last one is talking about the molecules being polar or nonpolar. Not the bonds, the molecules. So in this case on A, if you think about it, it's not going to have any poles because the tetrahedral shape, the chlorines aren't really going to be attracted to each other. So it's going to be nonpolar. This one's going to be nonpolar. Again, this one's going to be nonpolar. And this one's going to be polar because it's going to have more of a bent shape. Okay? And if you've made it this far, I want to congratulate you. And if there happens to be a random bonus question on the test that asks what my favorite Harry Styles song is from his new album, the answer is Cherry. Hopefully you get that right.